So what I'm going to do today is review complex numbers with you. And so I'm going to teach you or review with you how to convert between rectangular and polar, and how to use Euler's formula and the standard conventions, and we'll be doing most things by hand. Now, in the future, I won't do things by hand because I make too many mistakes to do things by hand. I use a calculator, and I use, for the most part for complex numbers, even though I have just about every calculator under the sun, and I like the TI Inspire CAS for most things. For dealing with complex numbers, I really like the TI 36X Pro. I know this says 30X Pro, but when you buy it, it's actually the 36X Pro. Just because it just makes things so much easier to do. And so for the future, I'm rarely going to work the complex calculations out by hand because I will make a mistake if I do that. I cannot add, subtract, multiply, divide. You have to keep an eye on me for that. So I have everything all nicely worked out today. Hopefully I don't, my problem is I'll start working it and I won't refer back to my notes, and then I'll make a mistake and people won't catch me. But I will do my best with that. And so we're going to start with a just an equation that we have to combine different forms and solve for V2. So this is something like y'all had in quiz 1. And it's supposed to be in phasor form. So on your first test and on some early quizzes, he may say, show your work and do not rely on the capabilities of your calculator. Later in the semester, he's not going to say that. So, but you do have to know it. You have to know this stuff. And so that's what we're going to do today, as much as I dislike it. Okay, so what you need to know about complex numbers in polar form is when we represent a complex number, we can use an axis system where we have a real axis and an imaginary axis. And so if I have a number like 4 minus J3, well, that is a number that in high school or in a math class, you would write that as 4 plus 3i, or 4 minus 3i. The I is the imaginary unit, and that's what your calculator has on it. Engineers use J because I is for current. And so 4 minus J3, I've never really understood why they put the J before the number, but they do. And I will sometimes not do that just because. And so if I wanted to graph this is saying it's 4 on the real axis and -3 on the imaginary axis. And so another way to think about this imaginary number is as that vector. And as that vector, vectors have a magnitude and a direction. And the magnitude would be the length of that vector, which we would get using the Pythagorean theorem. So that would be 4 squared, which is 16, plus 3 squared, which is 9, which is a square root of 25, which is 5. So that would be the magnitude. And the angle. And the angle, just by convention, not that it's right or wrong to not do this, but by convention, we use angles between 0 and -180 and between 0 and +180. And your calculator will give you the correct angle if you are in quadrants 1 or 2. But the calculator, when it does an inverse tangent, it only gives you the value for quadrant 1 or quadrant 2. Because the inverse tangent, if I were to take the inverse tangent of, if I'm trying to get this angle, this is +4, this is -3. If I take the inverse tangent of -3/4, can y'all do that on your calculator? And give it to me in degrees?
-36.86 degrees.
Oh, by the way, on this calculator, it likes to give you things exact, but as long as you have at least one decimal in your problem, it'll give it to you as a decimal. So like if I did inverse tangent of -3/4, okay, it gave it to me as a decimal. But if it ever gives you something like with square roots, the button right above the enter key, right there where my little cursor is, that turns it back and forth between exact and decimal. So like if I did inverse cosine of well, how about cosine? Cosine of 30 degrees, then it gives it to me like that. If I press that button, it gives it to me as a decimal, and if I did cosine, if I put even one decimal point in my problem, it'll give me the decimal answer. Just kind of hints for that. Okay, so what angle did you get?
-36.
-36 degrees. Is that correct for my problem right here?
For this one, yes.
Yes, for this one it is. Now, if I had this point right here, so if I had -4 plus J3, that's right here, and I, again, would do the inverse tangent of 3/-4, I would also get -36 degrees. Would that be correct for this point right here?
No, you need to add 180.
You would add 180. And so that's why it's important to be able to know what quadrant your complex number is in. Because if it's in quadrant 1 or 2, you're fine. If it's in, quadrant 1 or 4, you're fine. If it's in quadrant 2, when you take the inverse tangent, you would add 180. If it's in quadrant 3, when you take the inverse tangent, you would subtract 180. Because in quadrant 3, it would give you the one up here in this first quadrant. Now, the calculator, if you just are changing between rectangular and polar, it'll do just fine. So if I take -3 plus 4 -3 plus 4j second complex, convert to polar, 5 angle 126.8, and that's correct, because that's the one that's in the second quadrant. So like if I took that -36 plus 180, I see, I can't even use a calculator. -36 plus 180. Oh, I think I have this. I had this 3/4. I have 4/3 instead of 3/4. So anyway, it does work. Okay, so now going to problem 1. We're supposed to solve for V2 in phasor form, and we have a combination of things in polar and in rectangular. So it's easy to add, subtract rectangular, and it's easy to multiply, divide polar. So I have 3 plus J2, that's in rectangular form, times V1, which is 8 angle 90 degrees, plus negative 4 minus J5 times V2 equals 10. So to solve this, I want to look at it and I want to figure out, okay, do I want to do this in rectangular or do I want to do it in polar? And my answer, yes.
So for quadrant 2, you said add 180,
Yes.
and then what's the other quadrant?
Quadrant 3, you would subtract 180.
Okay.
Because what happens is, in the tangent is negative in this quadrant and this quadrant, and the tangent is positive in this quadrant and this quadrant. So if you take the inverse tangent of a positive number, it gives you the first quadrant answer. If it happened to be because you had a negative over a negative, then you subtract 180 to get this value. And if it's a negative, it'll give you this value, and you add 180 to get up to that one. All right, so I tend to use rectangular. I find it easier to work with. I know that a lot of electrical engineers will use more polar than rectangular, but you want to look at your problem and see what's easiest. Now that we understand what complex numbers are, if I look at 8 angle 90, that angle 90 tells me something really interesting, that it is just on the imaginary axis. Angle 90 tells me that it is just J8. It doesn't have a real part. And you would also get that answer if you're going from polar to rectangular, which I haven't shown you how to do yet. But I would take 3 plus J2, and I'm going to change this to J8, plus negative 4 minus J5 V2 equals 10. Because this multiplication is not hard to do. If I have two completely complex numbers that both have real and imaginary parts, I have to FOIL it out and everything, but this I just have to distribute. So it gets me J24 plus J squared 16 plus 4 minus J5 V2 equals 10. Now J squared, J is defined as the square root of negative 1. So J squared is negative 1. So most of the time I would not have done this step. I would have just gone straight to J24 minus 16 plus 4 minus J5 V2 equals 10. Now I'm going to subtract J24 minus 16 from both sides. So minus J24 minus 16 minus J24 minus 16. So on this side, I'm left with 4 minus J5 V2 equals 10 minus J24 plus 16, or 26 minus J24, 4 minus J5 V2. And I already have a mistake somewhere, and it was from copying the problem. It was minus 4 minus J5, and I lost my minus. So I was just copying the problem wrong, which I'm good at doing. Okay, so now, just like if I had 3x equals 24, I would divide both sides by 3. Here I'm going to divide both sides by minus 4 minus J5, minus 4 minus J5, and I get V2 equals 26 minus J24 over minus 4 minus J5. Now, once you get to start using your calculator, you'll just do this operation on your calculator and get your answer. But you can't leave it like this, and if you have to show all your work, this is not okay. You can't have a complex, you can't have an imaginary number in the denominator. So to get rid of the imaginary number in the denominator, you multiply by the conjugate, which would be minus 4 plus j5 over minus 4 plus j5. Now, anytime you multiply a complex number by its conjugate, something nice is going to happen. That's why we use it. So if I have a plus jb, the conjugate is a minus jb. Now, if I multiply this out, I get a squared minus jab plus jab minus j squared b. So the minus jab and the plus jab cancel, and I get a squared. And remember, j squared is -1, so minus j squared is +1, so I get a squared, that should have been b squared. A squared plus b squared. That's why I multiply by the conjugate, because it gets me a squared plus b squared. So when I multiply this by the conjugate, I have to FOIL the top, and when I do, I get -104 plus j130 plus j96 plus 120 over, and then in the denominator I get 16 plus 25. And then combining like terms, that gets me 16 plus j226 over 41, which is 16 over 41 plus j226 over 41. So now I need to change this to polar. So let me get these as decimals. This is 0.39 plus j 5.5. And so the magnitude is the square root of 0.39 squared plus 5.5 squared, which is, I don't know what it is on the inside, but when you take that square root, you get 5.53. And to get the angle, I take the inverse tangent of the imaginary part, 5.5 over 0.39, and I get 85.95 degrees. Now I need to decide if I need to add or subtract 180. So I look at my complex number. What quadrant is that complex number in? 0.35 plus j 5.5. 1. So do I need to do anything to my angle? No, it's good. So my answer is 5.3 angle 85.95 degrees. So any questions on that before I go on to the next one? Yes?
Wait, did you determine it was in quadrant 1 by getting the 85.95?
No. No, that does not tell me it's in quadrant 1. This tells me it's in either quadrant 1 or 3. The way I told was because I have 0.39 plus j 5.5. That tells me both the real part and the imaginary part are positive, and so it's here.
Gotcha.
Can you show how did you turn the polar to rectangular?
I am going to show that. I have not shown it yet.
Oh, okay.
Oh, I will show you for the specific one here, because it was a special case. So it was a special case because it was 8 angle 90. And so I said, all I said is we know that means angle 90 means it's on the imaginary axis, so it doesn't have a real part. But I haven't shown you yet how in general to do it.
That was my question.
Okay, yeah.
It's
So
like
we're
both
going to get to that. Yeah. As a matter of fact, we're going to get to that next, and I think I'll do that before I stop and save the recording, so that we have all of this on one. The one video kind of has all the basics. Okay, so this one says, form the following calculations and report your answer in phasor form. Okay, so I have, my number is minus 6e negative j30 plus 10 plus J4. All right, so this E negative J30, that's the same as writing -6 angle -30 degrees plus 10 plus J4. So I'm going to now show you how to change polar to rectangular. And this is Euler's identity. So Euler's identity tells us E to the I theta equals cosine theta plus j, e to the j theta, sorry, my math background was showing through, e to the j theta equals cosine theta plus j sine theta. And so this tells me that this particular one will be -6. And I always remember this because when I learned this in high school, we had a shortcut way of writing it. And so it's cosine, the imaginary unit sine, cis. And so just if you remember that order, that reminds you that it's cosine and then j sine. Just if you're forgetting which one goes with which. So 6 cosine -30 plus j sine -30 plus 10 plus j4. Now, you might or might not remember from previous math classes that the cosine of a negative angle is the same as the cosine of the angle, and the sine of a negative angle is the same as the negative sine of an angle. So if I have e to the j theta where theta is positive, then I just have cosine theta plus j sine theta. But if I have e to the minus j theta, that's the same as cosine theta minus j sine theta. Because if I put the minus in there, so if I had cosine negative theta plus j sine negative theta, this cosine negative theta is the same as cosine theta. The sine of negative theta is negative sine theta, so minus j sine theta. And so you sometimes can do that quickly. And so this is -6 cosine 30 degrees minus j sine 30 degrees plus 10 plus j4. And I'm sure you all remember your unit circle that the cosine of 30 degrees is square root of 3 over 2, and the sine of 30 degrees is 1/2 plus 10 plus j4, but you don't have to remember that. You have a calculator, and then you can calculate this out, and you get -3 square root 3 plus j3 plus 10 plus j4, which becomes 4.804 plus j7. So that's just finding the square roots and everything, or just, getting the numbers from the calculator. And then in phasor form, this will be the square root of 4.804 squared plus 7 squared. And our angle will be the inverse tangent of 7 over 4.804. Notice both of these are positive. Since they're both positive, but the angle that I get is going to be okay. So if my rectangular number is a minus jb, then that would be, so positive x, negative, that one is fine. If I have minus a plus jb, that's going to be where I add 180. And if I have minus a minus jb, that's going to be where I subtract 180 degrees. Okay, so when I find these numbers, I believe I get 8.48 angle 55.5 degrees.